Hello everyone. In this video, we are going to see in case of shell type transformer by changing orientation of the transformer winding, how to reduce the core requirement. Okay. So now let's say you have this shell type transformer with you, and this is the balanced current that is coming from source IA, IB, IC, and it is flowing through in these three ABC windings, you can say. And I have marked four section 1, section 2, section 3, and section 4. We will check what is the flux that is flowing through this all four section, and once we know the flux throughout all these sections, we can comment on the core requirement, because my flux density B is equals to 5 by A. Okay. And for constant flux density, flux is proportional to the area. So if in any of the section flux is flowing more, then in that particular section we need more area. Okay, so we will check this things. We will mathematically how to check and how to change or how to reduce the core requirement by changing the orientation of the windings. Now for phase A, you can say for phase A, phi A flux is getting produced. So phi A by 2 will flow in this path, and again phi A by 2 is flowing in this path. Okay. For section 2, you have phi B by 2 in this path, that is phi B by 2, and in this path, or in this direction I should say, I have flux that is phi A by 2. Okay. The same thing will happen here also, you can do that. And if you see this particular section 3, you have phi b by 2 in this direction, and phi c by 2 in this direction, phi c by 2. This is phi c by 2, this is phi b by 2, and again you have this phi c by 2. Okay, and you can check the flux that is flowing through these sections also. Now I have in section number 1 and section number 4, if I comment on section number 1 and section number 4, let's say section 1 and 4. Okay, section 1 and section 4, I have the flux phi a by 2, and in section 4 also I have flux phi c by 2. Okay, so magnitude wise, I can say like for section A or section 1, I have flux phi a by 2, which is nothing but if I take just magnitude, it is like this. So for section A, this much amount of flux is flowing. For section 4, it is phi c by 2, so it is phi m by 2 plus 120 degree. Okay, that's the phase difference. I'm just considering the phase difference also. But if you see this magnitude at section A and section 1 and section 4 are same, that is half of the phi m. So in these two section, I need the core in such a way that I need to pass this much amount of flux. But now analysis needs to be done in section number 2 and section number 3. Section 2 and 3. In both the cases, you can see one flux is flowing downward, another flux is flowing upward. So here also one flux is flowing downward, another flux is flowing upward. Now let's check on the section number 2. One flux is flowing downward direction, another is flowing in upward direction. So the net flux in section number 2, if I say net flux, that is phi a by 2 is flowing downward direction and another is flowing upward direction. So I should say minus of the phi b by 2 is flowing downward direction. So this is the resultant flux that is flowing in this region. Okay. Now I have to calculate what is the value. Obviously, these are the phasor what do you say calculations. So at section number 2, I have phi a by 2. Obviously, this is the phasor minus phi b by 2. Okay. Now take half common, phi m at an angle 0 minus phi m at an angle minus 120 degree. Okay. So if you calculate this one, you will get root 3 by 2 phi m at an angle of 30 degree. It is for section 2. If you calculate for section 3 also, you will get the same magnitude, but there will be difference in the phase. Okay, let me calculate for section 3 also. Uh, for section 3, you have this particular scenario: phi is equals to phi b by 2 minus phi c by 2. So phi is equals to half of phi b minus half of phi c, half phi m minus 120 degree minus phi m 120 degree. So if you calculate half of, what you will get? You will get 1 at an angle minus 120 degree minus 1 at an angle of 120 degree root 3 phi m minus 90 degree. Again, for section 2 and section 3, the magnitude of the flux is root 3 by 2 phi m. You can see there are two scenarios. This At this section 1 and section 4, we need core requirement less. There is less core requirement because my flux is also less, that is flowing phi m by 2. Whereas in section 2 and section 3, I have flux that is flowing, that is root 3 by 2 phi m. So obviously we need a more core in this section 2 and section 3. So it is a kind of non-uniformity has arrived. We have to come up with some solutions such that we can reduce this core additional core requirement. So we will see how to do that. Now let me erase the graph, erase the figure first. Mm, okay, okay. Now let's say I am injecting the current in phase B in this direction, IB. So the flux that gets produced in phase B, it will be in this direction. So here it will be phi B by 2, and in this direction it will be phi B by 2. So now you can see in section 2 and section 3, the flux direction is, it is a simple addition. So if I calculate what will be the net flux in section 2 and section 3 from this figure itself, let's say. So we have the net flux at section 2 as phi is equals to phi a by 2 plus phi b by 2. Obviously, these are the further additions. Okay. So if you calculate it, you'll get something like this. So calculate the net flux from here. Phi is equals to half phi m 0 plus phi m minus 120 degree. You will get 1 at an angle 0 plus 1 at an angle minus 120 degree. So you will get half phi m minus 60 degree. The same magnitude of flux you will get at section 3 also. Now our problem has resolved now. Uh, if we change the current directions or sense of the winding, if we change the sense of the winding for middle phase, we are getting some kind of uniform flux throughout all the sections, section 1, section 2, section 3, section 4. So there is a reduction of the core, and there is a uniformity in the flux and in terms of core material also. So this is how, by changing the orientation or changing the current direction of the middle phase or phase B, we can reduce the core requirement and all. Okay, I hope this analysis is clear. And if you have any doubt, you can ask me in the chat box. Thank you.